everyone coming to this community. So I think I'm also kind of a visitor here because I'm mostly based in Kyoto, so I sometimes come here. And so, as Nalasan requested me to give this lunch seminar, and so I'm talking about something about quantum chaos, some basic things which might be um, simple to understand for a diverse audience here, not very particular details. And the title I told is that some quantum chaos is non-Hermitian systems which are currently working at this moment. But to go beyond, we need some basic preliminary to understand what is the actual thing in Hermitian systems. If you remember a few weeks back, Gabriel did a nice talk, and he mostly talked about from the quantum gravity perspective. And also, I'm talking about mostly the quantum many-body systems, but both things are quite related. So, yeah, if you want to know about the
If you can hear us in the common room, we cannot hear you anymore. We lost the sound.
Oh, sorry.
Oh, yeah.
Can you hear me now?
Now we can hear you. Thank you.
Okay. So I haven't really started. So first I'm going to describe what is classical chaos because it's very well defined. So to understand this classical chaos, so I'll start some simple, some initial point and follow some trajectory of some particle. So these two are the two particles. Suppose we follow the yellow line. You can see this is bounces back and everywhere in the board. Suppose it's completely like reflecting boundary conditions. So anything goes back. So it just stays inside this. And suppose you turn this is the one of the trajectory you can see the particle. And suppose it's part of initial condition of the particle. So you get this blue trajectory. And if you part up initially only a tiny amount, you can see at a large time, late time, the two trajectories are completely different. So in the context of the space, what you remember your classical mechanics, if you some phase-space coordinate, this is like how the deviation looks like how the later time is from if you do some initial perturbation of the earlier time, and trajectory goes exponentially. And this is usually the classical Lyapunov exponent. That's one of the crude way to define classical chaos. These things, everything is well defined because trajectories are very well defined in classical system. But now there's many aspects of the classical chaos. I'm not going into the details, but if I want to map to the quantum chaos from this picture, we run in several problems. First of all, but there is no appropriate definition of the phase space in purely quantum system. We have some semi-classical system, we have some description, but not fully quantum system. So how do you translate to this phase space in quantum system? And what is meaning of this small perturbation in the quantum mechanics? There's many questions. As I said, semi-classical or Largian systems, or we usually talk about quantum gravity in this regime. There are some there you can translate some of the aspects of these things to your study, but in a fully quantum system, this picture is changed. So you need some different way to describe the quantum chaos. It's a chaos in quantum domain. So that's you call quantum chaos. Definition is not very certain what definition we should use, but there are some things we should come up so that I can describe some chaotic things. So that if I go in the classical regime from the quantum regime, I get back to all of the description that I get. So to describe a fully quantum mechanical description, so usually in medieval systems we mostly talk about the Hamiltonian of the system in the finite dimensional metrics of the Hamiltonian. So how do I describe quantum chaos from that perspective? So as system is described by a Hamiltonian, there are different probes to describe the quantum chaos. One is the direct probes. The direct means I'm only relying about the Hamiltonian itself, not anything other than the Hamiltonian. Okay. And this probes basically means eigenvalue correlations. How my eigenvalues are correlated among. So if eigenvalues are correlated, I'm going to describe that those are kind of feature of the quantum chaos. Okay. And this correlation can be short range or can be long range. There are different conjectures among these correlations, mostly in the context of random matrix theory. Because random matrices, I have also a Hamiltonian, which is completely random. So I can want to map how my Hamiltonian, system Hamiltonian, maps with the random matrix Hamiltonian. There are certain conjectures, and there is some sort of indirect probes. And this indirect probes, basically you insert an operator in your system, and you want some local operator, local perturbation, in the sense that this small perturbation is the context. Just add a simple operator in your system, and you want to see how the operator grows if time flows, how the operator evolves, like a Heisenberg evolution. So that means if I insert some information of the system, how the information flows across the full system. It's like it's usually called quantum scrambling. How my information scrambles throughout the system. And this context, many things comes along, especially in the context of gravity, like in black holes and other sort of things in this context. So there are different notions of operator growth, and this is also something called probabilistic definition for mathematics. If someone is mathematically oriented, this is some recent interest of quantum chaos. I'm also interested of this aspect recently. The probabilistic description of the defined quantum chaos. And there's different notions like a size distribution, out of time order, correlator, complexity, and many other ways to define how you want to probe chaos in your quantum system. Okay, so today I'm going to talk about only this kind of direct probes. It's a kind of simpler to talk about. So it is visible, right? Okay, yeah. So suppose I have the Hamiltonian for my system, and it's a finite dimensional. I always talk about some finite dimensional Hamiltonian n cross n, and usually I take n is a bit large, but numerically tractable quantity. Large, okay. And I have an eigenvalues, set of eigenvalues, lambda n, and for the moment, let's consider only non-degenerate eigenvalues. And we do some, this I forgot to mention, is like I will set int lambda 1, 2. So I form an ordered set. So because this is numbers, Hamiltonian, we have already real eigenvalues. So I just form an ordered set of these Hamiltonians, small to large, and want to study how these eigenvalues are correlated. Okay. So when I sort about these eigenvalues, I don't know. So what I study how the nearest eigenvalues are correlated, not the farthest. I can also talk about the farthest. Let's talk about the nearest eigenvalue correlated. So what I define some spacing of the nearest eigenvalues. Let's just take to nearest eigenvalue. And I get n minus 1 sort of list. And I want to set the histogram of the list. How this histogram? So it turns out that if you do this kind of analysis in random matrix theory, there's a very universal description. So this is one of the universal known results, analytic results for random matrices, which means that which will show that there are 3 classes of random matrices that you can talk about from the symmetries of the Hamiltonian, which basically mimics the symmetries of your system, like time reversal, time, very different system. So there are 3 kind of random matrix universality classes that you can describe in this random matrix theory, and they follow their nice distribution this kind of distribution. This is the histogram of your eigenvalue spacing. Okay, there is something called GOE, is Gaussian matrices, Gaussian orthogonal ensemble, Gaussian unitary ensemble, and symplectic ensemble is basically how I describe the elements of my Hamiltonian, whether they are real, whether they are complex, or they are quaternion, different structure. Of there are three kind of universal structure, and all these cases you can see this they go some proportional to spacing as your spacing turns 0. This is a very important result, which is not very visible here for some reason. Important, which means that as you go in this region, you see there is almost like a 0. That means your nearest level repulse. There is a 0, almost like a very small probability of your eigenvalue correlation to stay very near. So this is one of the defining feature of the quantum chaos, that your nearest level repels. Like if you distribute your eigenvalues in this way, you see there is almost there is no congestion of your eigenvalues. On the other hand, if you have a system where eigenvalues are uncorrelated, you will get this kind of red plot, which is basically exponential of -s, and you can see that at s equals to 0, this is 1. Okay, that means your eigenvalues are physically trapped, so they are congested in a certain region. So your uncorrelated level can have a congestion in your eigenvalues, while in a chaotic system you have this kind of repulsion. So this is one of the defining features of the quantum chaos in the chaos in quantum systems. So the universality statement is that your chaotic systems follow this RMT spectra. So given your Hamiltonian, you compute this and you check whether your Hamiltonian follows this kind of description. And if it does, in most of the cases, there are some anomalous cases also, but we understand why this happens. But mostly, you can say this kind of feature happens in your system. So you define your systems are chaotic and non-chaotic. And this is a very universal description, because you can define all the symmetry classes dynamics from this kind of description. This is kind of very accepted definition of the quantum chaos, and people are mostly finding this kind of things. And I think one of the reviews are this review on the book here, which is a very nice description of this thing. So this is what happens in a Hermitian systems. So now I will go to some non-Hermitian systems that one of the title I mentioned. So this I have to write here because I have spaces. But mostly the thing is simple. So now I take some non-Hermitian Hamiltonian. The importance of non-Hermitian Hamiltonian is that they are often encountered in the context of open quantum system, like a distributive system. Your system is like has some connected to some at the bottom of the system, which is when the real systems happen. The information flows through the system, and your evolution is no longer unitary, because if you remember, unitary evolution is basically given by like e to the power iht, and by the definition of u dagger u equals to 1, it requires a Hamiltonian to be Hermitian. But Hamiltonian non-Hermitian evolution is non-unitary. So when your non-unitary evolution cases, you often describe with some Hamiltonian and non-Hermitian Hamiltonian, which is very recent interest, and people have discovered experimental fact these days as well. So if I have Hamiltonian is non-Hermitian, how I'm going to translate those features in a chaos? First, we immediately run into a trouble in the first case, like this kind of eigenvalues. Eigenvalues are complex, right? So r e to the power I theta, some complex zero. And how do we find an ordered set from a complex number? It just doesn't make sense. So you run into trouble. So there's one way you can do is that you find an ordered set of r, the magnitude of your number, and run the same course. So now your eigenvalues are distributed on the complex plane, right? Not a real. Previously there was a real line, and you define ordered set. So now you define into a complex plane. So R R1 and R2. You can set an order, but you can see there's also an order from here, same distance R1 R2. So you need the theta as well. So you define two order sets. One is from the R and one is from the theta. And often this has some very numerical challenges in numerical computation because you are now doing like a double computation to describe the system. And often the results are not very universal in this description. But still, people have studied some of the aspects, how you define some of the classification. Mostly in 2019, started in 2019, and there's many results these days. The study. So people are trying to understand, is there a simplified description of this picture? Can it escape this kind of picture and actually describe something in a real line? One variable, not two variables. It turns out that the answer is yes. So it was very recently found, like 2023, that instead of the eigenvalues, so you need to think, you need to go beyond the eigenvalues. Because initially we thought, okay, the eigenvalues are correlated, they are the defining feature of the Q. But it turns out that in non-Hermitian cases, you talk about the singular values of the Hamiltonian, not the eigenvalues. So if you remember, I will just briefly tell about this is Hermitian cases. Let's say this is my decomposition, right? Hamiltonian is decomposed from diagonal matrix or some unitary matrix. W dagger W equals to 1, Hermitian cases. But in non-Hermitian cases, you can define something, the singular value decomposition. This kind of decomposition is, we know from the quantum mechanics, and these things both are unitary. U dagger 1 and V dagger P equals to 1, but they themselves not unit, they can come from the unitary. And this eigenvalues this is the diagonal matrix. Because previously this is a diagonal matrix, so we write with the eigenvalues. This is also a diagonal matrix, and the elements are known as singular values. And the defining feature and the interesting feature of this Hamiltonian is singular value decomposition, for SVD, is that they're all real. They're all real elements. So you can ask that question: can we describe the correlations in terms of the singular values of the Hamiltonian? Is it possible? So it turns out that it is indeed possible. So what you do, you decompose your Hamiltonian, non-Hermitian Hamiltonian, in a singular value decomposition and pick the numbers from here, and you run the same course. You don't need to change any prescription, just run the same course, and you get exactly the same feature of your Hamiltonian. So you run, okay, it's very nice. I can go to the very university, all the symmetry classification, and you can describe by a singular decomposition, which is very hard and very obscure in this definition. So people are thinking, oh, this very nice thing, description, like the definition of the chaos turns out is more general than the eigenvalues. It's like how the singular values of the Hamiltonian. So now you can ask the question, what happens if a Hamiltonian is Hermitian? Can you describe in terms of singular values as well? It turns out that for a Hermitian limit, your eigenvalues, singular values, reduces to your absolute values of the eigenvalues. So in that case, you can also describe in your chaos and quantum system. So that's the idea is that instead of eigenvalues, which was kind of defining feature of the quantum chaos for several last decades, is slowly going to the concept of the singular value decomposition. And this is kind of decomposition is also very useful in quantum state preparation, other kind of quantum computing thing. And interestingly, also people have discovered that you can define the entanglement spectra using these singular values as well. And you can extract like central charge of your CFTs, non-unitary CFTs, and they're very well matched to your theoretical prediction. So this kind of thing things are very new direction to your system. How much time I have left, or is it just over?
Actually, you ran out of time already.
Okay. So just I'll let 1 minute maybe.
Yes.
Okay. 1 minute, is it okay? Okay. So if you are interested in study of quantum chaos, and you could take a very simple system, Hamiltonian, generated in Mathematica, very simple Hamiltonian matrices, and study is how these properties are translated there, and I think if you are doing some statistical data analysis and stuff, and you are interested how my data are folded or unfolded, you can run on some similar statistical distribution of this kind and try to apply this distribution. But these are very simple way to understand the physics. But you have more sophisticated techniques, and if you have any other questions, I'm happy to discuss about this more. Thank you very much.
Okay, thank you very much, Pratik, for very interesting talk. Okay, the questions?
Session. Hamiltonian is just some operator, which is not assumed to be. It's not assumed to be a real operator, complex operator, right?
I'm assuming it's a Hermitian or non-Hermitian operator.
Yeah. So assuming it's not Hermitian, you're not assuming that it also has real entries.
Yes.
And then later you say that you have the SVG decomposition in which U and V are Hermitian.
No, that's unitary.
Oh,
unitary.
Okay, unitary.
This is Hermitian. This is non-Hermitian. This is non-Hermitian. You can also do the Hermitian analysis. If it becomes Hermitian, then U and V equals equal. U becomes V. So you get back to the same picture. Yeah, please.
Is there any classical analog of a non-Hermitian classical chaos?
Non-Hermitian. So I haven't seen, but I think some people are trying to understand how this picture relates to some classical description of chaos, but it's not very apparent at this moment.
Thank you.
Any question? Since you said Hamiltonian, you can have classical dynamics always.
Yes.
So can you discuss the chaos in classical dynamics in this case, or
No, in non-Hermitian cases? Okay, so actually don't know the answer, but usually this hermiticity, this kind of question arises in the purely quantum regime. But if you go to your classical system, yeah, I don't know the answer, but I will take a look at this description.
Well, so what do you expect is different between the chaos in Hermitian case and non-Hermitian case? Do you expect the new universality class or?
Yes, so there are several aspects. One is that, for example, the symmetry classification you have been told. In Hermitian cases, there are 10 symmetry classes. These are the 3 symmetry classes, and there are also 7 other symmetry classes. So there are total 10 symmetry classes called Ortland-Zinn-Bauer symmetry classification. But in non-Hermitian cases, there are 38 classes. The symmetry classes enriched much more beyond this tenfold. 38 classes. And there are some localization properties, like a many-body localization properties. In non-Hermitian cases, you observe some very different phenomena called skin effect, which is basically how your basically this is the behavior in the boundary of your system. In Hermitian cases, you don't see such behavior. So something known as skin effect. This kind of behavior very special to the non-Hermitian systems. So localization properties, many-body localization properties, and other properties, symmetries are very different entirely from in the non-Hermitian cases. It's more generic.
And well, you mentioned that some of the non-Hermitian systems can be obtained by attaching some kind of environment.
Yes.
Yeah. So then I wonder so if we look at the total system, then it's Hermitian.
Yes, you're right.
So that the total system is described, so for example, classified by 10 universality classes.
Okay, yes.
And in that case, why well, if we look at only a part of the system, why does number of universality classes will become larger? What's the mechanism to?
So when you describe your certain part of the system, you basically kind of trace out the other part of the system. The information is lost.
Yeah.
So you don't have access to those systems. So you are very confined to some certain systems, which are, for example, are not unitary. The full system is unitary, but the certain system is non-unitary. So the symmetry classification entirely comes from your this 38-fold classification comes from your these two kind of eigenvalues, this r and theta, and also they are encoded in the secretly in the singular values. It's very secretly. So in Hermitian system, these eigenvalues are absolute values of their singular values. So you take the modulus. So if you denote it's a sigma 1 and this is a lambda 1, so this sigma lambda 1 is basically the absolute value of the sigma 1. So there you are basically missing some certain kind of symmetries of your system. If you describe here, go here.
Yes, where I can, well, mathematically I can guess that something different may happen for a non-Hamiltonian. But very naively thinking, well, if that universality class can be encoded in the structure of energy eigenvalue, then why? Well, when we look at only a part of the system, the behavior can change. That's my very naive question. Maybe where for the if the total system is chaotic, then I think where the universality class must be the same. But if maybe where the non-Hermitian doesn't mean that
you lost the constraint. In Hermitian cases, you have constraint. H diagonal equals to H. In non-Hermitian cases, you don't have a constraint.
Yeah. So mathematically, where I can imagine where. Yeah.
So the symmetries gets enriched because you lose some of the constraint, and this constraint will basically reduces to your symmetry from 38 to 10. So you can ask why this 38 number comes from, but that's a mathematical. But it's like unitary system is a more constrained system. Non-Hermitian systems are less constrained. So that's why you need to describe with the more symmetry in general.
In statistical mechanics or field theory, we measure or evaluate correlation functions or scattering amplitude. What do you evaluate in the chaos theory? You also measure evaluate correlation functions. Or what do you evaluate?
Okay. We can define correlation functions in case of, for example, in this kind of indirect probes. So I have an operator, some operator. So I can describe some operator OT and O. This kind of correlation, OT and OT is basically my I can have my AHT O e to the power minus IHT. It's like a Heisenberg evolution of OT, and this is my initial operator time t equal to 0. So, and I define the correlation function. I can define endpoint also. The 2 points simple. You can define correlation function. So the correlation function defined in terms of the operator. There is some particular behavior of the operator. This kind of 2-point function or 4-point function in my chaotic system. This is like an OTOC. How my 4-point function, 4-point function describes in this cases. So I can define the correlation function in this picture. Yes, please.
I'm curious, let's assume we start with a closed system, which is chaotic, a quantum system, and now there are many ways how to couple it to an environment. Does it necessarily stay chaotic in this more generalized non-Hermitian sense, or does it depend on how I construct the environment?
Yes. So it depends how if you have a system and you attach to some environment. So it depends on the coupling, whether your coupling is small, weak. So for example, if you if your coupling is small, you can describe mostly in the chaotic phase, but there is pure small dissipative phase in the case so that your information leaks to the environment. And that is if you are in a purely dissipative phase, like your coupling is very big, very huge compared to the system's inherent coupling, inherent parameter. There are two parameters. One is the coupling, and there's some systems say inherent parameter J. So depending on the J, this limit or U this limit, you can describe completely fully system phase or a dissipative phase, and there's a transition between these two phases. Very recently, people have found this kind of transition, and many of these cases you can study mostly analytically in the regime where your coupling is small compared to the system's parameter, because you get some sort of Markovian approximation in this case. But beyond this regime, you have a non-Markovian system, which is very difficult to handle. So of course, it depends on the coupling and how from the coupling to the system and the environment.
Sorry, I'm confused. What would be a non-Markovian, non-Hermitian Hamiltonian?
Yes.
What
So
would be, I mean, I'm not aware of this distinction.
yeah, what cases are non-Hermitian?
So this does exist or?
Yes. So Markovian means that I don't have the memory of the environment of my state. The non-Markovian means that I have a memory. I have a memory effect.
I agree, but for that you need the Maxwell equation.
Yes, exactly.
But you're talking about non-Hermitian.
Yeah, so the master equation, you can write the master equation in terms of a non-Hermitian Hamiltonian, the Lindblad master equation. So I'm talking about that non-Hermitian Hamiltonian.
Okay, but then you have on top of the non-Hermitian Hamiltonian also other contributions to the dynamics, the jump operators.
Yeah. There are other operators, of course.
Okay, but then you have a different formula.
Yeah, different formalism. So okay, depends how your interaction to the environment is. You can go to the Markovian limit and non-Markovian limit, and from that limit you would describe your effective Hamiltonian. This is my Hamiltonian, not the system Hamiltonian. The effective Hamiltonian that I'm describing this full system, not the full system, only this system. So it's an effective Hamiltonian. That Hamiltonian is a non-Hermitian Hamiltonian. If you write a full Hamiltonian with system and bath plus interaction, that is definitely a Hermitian Hamiltonian because the system is unitary. But you are only focusing on this Hamiltonian, then your Hamiltonian becomes non-Hermitian in the Lindblad formalism. Master equation.
Yeah, I agree, but let's assume you have like a system, an open system described by Lindblad master equation. So we have this description by an effective Hamiltonian, which is non-Hermitian. And let's assume the closed system would be chaotic. Is then the system described by the non-Hermitian Hamiltonian necessarily also chaotic?
Yeah, that's what you expect, because ultimately system so how we describe a chaos is that I have a system. I know it is chaotic. I want to attach to a system in the bath, but my system is still chaotic. So I want to describe my system such a way that in the presence of the bath, I can describe my chaotic system. My system is chaotic. This is chaotic. My system is chaotic. I do not know about what is the bath, what is the environment is. My system is chaotic. I can describe everything here. Now I attach to a bath. Now my information is flowing. I cannot apply all this formalism. I want to define a new formalism such that I can describe the chaos. I keep the chaotic features of my systems.
I agree.
That is the.
I think my question is more in the direction I want to get an intuition. What would it mean that the open system dynamics is chaotic?
Chaotic, yes.
Basically, has an open system dynamics.
Yes.
But open system is just that if I have an open system, generically I would assume that large times my system runs into a steady state, and that kind of doesn't harmonize with my understanding of.
So you mean your system thermalizes with the
any initial state eventually converges to the steady state if you have a unique steady state.
Yeah, you can still describe this.
In that case, I would not talk about the chaotic system.
This case you do not, but your initial system was chaotic, right? Your system is
Exactly.
Yeah.
The closed system is chaotic, but I can construct an environment such that I run into it.
you can go to a steady
Unique.
Unique steady state, yes.
Of the initial state.
Yes.
I can just have don't see how this harmonizes the concept of chaos.
So you see there are some classical description arises like from this because it's thermodynamic systems. The chaos is lost. That's
I mean, in my understanding, you can do your level spacing analysis and
Yes.
your distribution, but I mean, what I see physically is just that all initial states running in the same in steady state. Yeah, I'm just wondering if I would call it chaotic or not.
I think it does.
Not necessarily, but I mean, I have a lot of freedom of how I can construct environments, and I can, for any closed system, I can always construct an environment such that are running to a unique steady state.
so there are formalism is that instead of considering the eigenvalues of the Hamiltonian, you consider the Lindbladian master equation, the Lindbladian is a double Hilbert space, and you study the properties of eigenvalues properties of the Lindbladian. So there is some universal description of the eigenvalues of the Lindbladian because Lindbladian you write in presence of the environment. So the environmental information goes into the Lindbladian, right? Because in the master equation. And this eigenvalues of the Lindbladian, if they follow some universal feature, you call that my system is chaotic in the context of the presence of the environment. So this the defining features are the same. Defining features are the same. So instead of Hamiltonian, sometimes you in the master equation you consider the Lindbladian of the Hamiltonian, and you replace everything, and you just everything follows. You just change the operator. That's one of the goal to keep most of the things consistent, just to change something in the level of the thing and get the similar description.
Actually, the Lindbladian itself is also not a mission.
Yes, right, exactly right. Yes, yeah. So you do everything in the level of the Lindbladian.
Of course, in the level of the Lindbladian, the same argument holds that you can construct the Lindbladian in a way that you run into unique steady state. Yeah, and that's why my question would be, I mean, if the formalism can distinguish, so to speak, cases where I run into unique steady state, which I would maybe not call chaos, but the level spacing would still tell me this is a chaotic system, then I would be kind of confused.
Okay, let's talk about this. I'd like to understand it more.
Yeah.
Okay, so
Well, maybe I just want to ask. It's nice to have the non-Hermitian Hamiltonian, but in view of the relativity, you might have considered the non-Hermitian momentum or something like that. That's not interesting at all, or because of the relativity. Non-Hermitian Hamiltonian might imply non-Hermitian momentum or like that, but that's not interesting.
I think I don't have these ideas about the non-Hermitian momentum in the relativity.
Well, but for example, uncertainty relation might be influenced if you consider the non-Hermitian momentum, for example. P and X are usually regarded as a Hermitian operator, right, to derive the uncertainty relation. But if you lose that kind of constraint, uncertainty relation might also be modified a lot, or maybe nothing interesting. I don't know.
Sorry, I do not know the answer.
Oh, I see. Okay, thank you very much.
okay, so let's wrap it up and thank again the Pratik for very interesting and stimulating talk. Thank you very much, and thank you for participating in the discussion.